In this video, I will teach you introduction, structure of alkene, reactivity of alkene, chemical reactions, and isomerism of alkene. Okay, isomerism of alkene. Okay. So at the end, I will upload these my notes on my website on11.com, from where you can download and get help. Okay. So let's start from the alkene, introduction of alkene. Okay. As you know, like alkenes, they are also known as olefins. Okay, oil forming. Okay, they are also known as olefins. Olefins mean they are oil forming. Okay, you know, unsaturated hydrocarbons, for example, like plant oils. Okay, alkenes is unsaturated. It is from unsaturated hydrocarbons. Okay, sorry for background noise. Okay, unsaturated, they are oil forming because majority of your plant oil, your cooking oils, olive oil, okay, just like this, they are actually unsaturated in nature. So it is the reason they are also known as alkenes, are known as olefins. Okay, oil forming. So number one, alkenes, they are unsaturated hydrocarbons, and you know this carbon to carbon minimum one double bond is present. If this minimum one carbon to carbon double bond is present, that compound is known as alkene. Okay, and if you see their name, they ends with, like their suffix, last name of alkene. Okay, they ends with ene. Ene mean when there's some double bond. Okay, and what about their general formula? You can see general formula for alkene, it is CnH2n. Okay, in alkane we discussed the general formula is CnH2n plus 2, but why two hydrogens are less here? Because you are making double bond here. Okay, it is the reason two hydrogens are less here. Okay, so how can we use this formula? For example, CnH2n plus 2. For example, if you have like hexene, okay, hexamine, when there are carbons are 6 carbons. Okay, so when you have 6 carbons there, so put this like n is equal to number of carbons. N is equal to number of carbons. Okay, so now you can see it here, like if C6H2, instead of n I'm writing this 6, it will become, you know, C6H12. Okay, so you can easily figure out, like ratio is 6:12 between atoms of carbon and hydrogen. You can simplify it 1:2. So if there is 1:2, you can easily figure out that must be alkene. Okay, but not always, so be careful. Okay, so if we talk about structure of alkene, okay, if we talk about its structure of alkene, you know, alkene is like it contains carbon to carbon double bond. For example, if I have this carbon to carbon double bond, it is connected with two other hydrogens. Okay, and now you can see, like one of the bond is like sigma bond. First bond is always the sigma bond. Okay, stronger in nature, and the other bond is pi bond, which is weaker as compared to sigma bond. So they all are sigma bonds. Okay, carbon to hydrogens, they all are sigma bonds. If I like teach you about this hybridization, so now you people can see it is sp2 hybridized. Alkene is actually, sorry, you can see it here, it is sp2 hybridized. Okay, alkene's hybridization is sp2. It means 1s and 2p. For example, we have this px orbital at the x-axis, and you have py. Okay, as you have this pz. Okay, understand? It means py pz. sp2 mean this 1s and 2p, they are intermixing together, they are like hybridizing. They are 3 in number, so you will get 3 new hybrid orbitals, 1 2 and 3. So what is actually hybridization? Hybridization is intermixing of these orbitals, okay? Before hybridization, you people can see they are different in shape with different energy. But when they will intermix together, okay, so they will produce equivalent numbers. Equivalent mean the number of taking part and number of produced, they must be same. There are 3 orbitals in before mixing, and there are 3 orbitals after that mixing. Is it clear? So this phenomenon is known as hybridization. But here you can see one of the orbital, it is unhybrid PZ. It is not taking part in the hybridization process. Okay, so how can I draw this structure in orbital way? So you can see it is a 1 carbon. Now it has 3 hybrid orbitals. They are known as hybrid orbitals. Even in your syllabus, you can see it in A levels. They are known as degenerate. They are known as degenerate orbitals. Orbitals having same energy. How to define them? Orbitals having same energy but different axes. Orbitals having same energy but different axes. Okay, so px, py, pz, they have, when they have same energy, before mixing they have different energy, after mixing they have same shape and same energy, so they are hybrid degenerate orbitals having same energy. Okay, so now you can say this carbon is having 3, so 1 hybrid orbital, second hybrid, and now it is the third hybrid. Okay, so same thing for other carbon. You can see it is first hybrid orbital, it is the second, and it is the third one. Okay, so now you know hydrogen has only one, like it is 1s1. You know hydrogen is s spherical in shape, so its configuration of hydrogen is 1s1. It means there's one electron, so it is overlapping with this sp2 hybrid. It will become, like sp2 making a bond overlapping with this s. Okay, so same thing for this, same thing for third one, and same thing is for the fourth one. Okay, so how can you write this? It means one of the sp2 hybridized orbital, it is overlapping with other sp2 hybrid orbital. Okay, is it clear now? So they all are sigma bonds. Okay, when there is head to head overlapping, it is a sigma bond and it is a stronger bond. Okay, reason is you can see this electron pair, shared electron pair, one of the electron of this carbon and another electron of this carbon. Now this shared electron pair is actually experiencing effect of nuclei of both carbons, nucleus of this carbon as well as nucleus of this carbon. They both nuclei are influencing this lone pair. Okay, this shared pair of electrons. Okay, so what about this PZ, which is unhybrid in nature, which is not taking part in this reaction? Okay, so this unhybrid, it will remain here as an unhybrid. You can see with the red color, it is a PZ which is like shaded. I'm representing as a shaded unhybrid. So you can see it here as well, PZ. So when this unhybrid orbital, when they side to side are parallel or sideways, okay, when they sideways parallel with each other, they will develop a pi bond. It is a weak bond, and it is the reason alkenes are more reactive than alkanes. Okay, it is the reason alkenes are more reactive than alkanes. And now you can see above the plane, like they are making, you can see it here, this bond, and you can see here this bond. Okay, above the plane, if I pass through a plane, you can see, for example, I am passing a plane with this, it is a plane, okay, passing from here. So now you can see electron density over the plane and below the plane. Okay, electron density of pi electrons is over the plane and below the plane. Okay, so let me draw the structure for you is. So now you can see there's a carbon, it's a sigma bond of carbon, is it? Another sigma bond with this hydrogen and with this hydrogen. Okay, and here, and now you can say like it's the electron density above the plane because of pi electrons, that pi, and below the plane. Okay, I hope you got this point. Okay, so electron density is higher here because there's a pi electrons. It is the reason alkene is more reactive than alkenes. Okay, alkene is alkene is more reactive. Alkene is more reactive than alkanes. Okay, because in alkanes they are saturated. There's no such a pi bond. Okay, so I hope you got this answer and understand its structure. And now I will teach you about their chemical reactions, and I will teach you how this structure influence chemical reactivity. Is it clear? So we are proceeding next. So now I will talk about reactivity. So reactivity of alkene is simple, as I already told you, like this carbon to carbon double bond. Okay, it's connected with some hydrogens. And here is, you can see some E for electrophile. What is electrophile? What is a nucleophile? I have another video, difference between electrophile and nucleophile. So you can see that. Okay. So electrophile mean it is positively charged and it is electron deficient species. Okay. Suppose it is a negative one. So here I already told you electron density is higher because of these pi electrons. Okay. So the electron, they are now like attacking over this electrophile. And now you can see electron of this electrophile and this B, they both are moving towards this B. Understand? So the pi electrons are being involved for this reaction. So this pi bond will break. It is the reason these reactions are known as electrophilic. These reactions are known as electrophilic addition reactions. So now you can see easily, like the bond will break from here, carbon, this carbon, and pi bond is break down here. So that E electrophile is being attached here. So now you can see this carbon is making 3 bonds. Okay, so this is known as carbocation. When carbon bearing positive charge, it's like you can see there's no electron in the carbon. Then where is that electron? So you can see this electron of this carbon and this. They both are like involved in making bond with this electrophile. Okay, so electron pair is being used here. So this situation is known as carbocation. Okay, so now you can see this B negative. Okay, this B negative now with lone pair of electron. Okay, the species which contain lone pair of electron or negative charge, it might be negative, might be neutral. Okay, it behaves as a nucleophile because it loves the nucleus. So here you can see it is attacking this nucleus like positive charge, and there is electrophile. So now you will get this, the final answer. You will get this like carbon with attached with this B, and here you can see. Understand? So type of reactions, actually they are known as electrophilic substitution reactions. Okay, so they are actually known as electrophilic substitution reaction. Electrophilic electrophilic substitution reactions. Okay, my bad. They are known as electrophilic addition reaction because double bond is broken. Electrophilic addition reactions. Okay, so the next topic is we will talk about chemical reactions of alkene. Okay, reactions of alkene. Reactions of alkene. In today's video, we will talk about like reaction with chlorine or bromine, reaction with chlorine or bromine, especially bromine. Especially I will teach you about bromine, not with the chlorine. Okay. Second, we will talk about reaction with steam. Okay, reaction with steam. Okay, and third, I will teach you about, you can say, oxidation reaction of alkene. Okay, oxidation reaction of alkene. So like steam is like, you can see it is a hydration reaction, is it? You can say it is hydration reaction. Okay, so we will cover these reactions, and I will try my best to explain these reactions in detail. So if he gives something else instead of these, then you will also be able to tackle the question, okay, with their mechanisms, inshallah. So first cause reaction is reaction with bromine, okay. So bromine is reaction with bromine, halogen, reaction with bromine, okay. So the first question is, bromine is not a like reactor species. You can see bromine is like Br2 molecule. It is not bearing any positive charge or it is not bearing any negative charge. It is a non-polar species. It is not polar mean when something has negative charge and positive charge, okay. But you can see both bromine atoms are same and there's no such a charge, okay. But the thing is, when this bromine molecule comes close to this alkene, when bromine molecule approach this alkene family, so the density of this pi electrons, it slightly induces its polarity, okay. Is it clear? The density of this pi electrons, it slightly induces its polarity. So when it slightly induces polarity, one of the bromine will bear slightly positive charge and other will bear slightly negative charge. Is it? So the thing is, then this pi electron, they will attract over this electron deficient bromine, like the positive one, which is electron slightly electron, not completely. This partial mean slightly charged, okay? It means slightly positive, okay? So now when this will happen, electron of this bromine and this bromine, both the electron, they will move toward this bromine, okay. So now what will you get now? So you will get this, here you can see, so this pi bond will break down, okay. So you will just get this one hydrogen here, other hydrogen here, so bromine will attach here, okay. And you can see other hydrogen and this hydrogen. So now you can see this bromine, it will, here you can see this carbon is bearing three charge, three bond, 1, 2 and 3. So it is bearing positive charge because it is without its electron, okay. So it is it is known as carbocation. It is known as carbocation. And this Br negative, that Br negative, okay, it will attack over this, okay. It will combine here and then you will get this, you will get this carbon to carbon, bromine here, other bromine here, and now you will get this hydrogen and hydrogen, okay. So it is your result. So the next question with some rule, Markovnikov rule. So the reaction with HBr, reaction with HBr, okay. Now you can see like you have some alkene, carbon to carbon double bond is there. Here you can see it is connected with these hydrogens and it is being react with HBr, okay, hydrogen bromide. So if you see, Now it is electrophile. You can see it here. It is an electrophile. It's a nucleophile end. Okay. So this pi electron will attack over here as usual. This pi electron will attack over here. But now the question is, sir, this hydrogen positive will it connect with this carbon because it is also connected with the double bond, or it will connect with this carbon because it is also the part of this double bond. Addition will happen on this double bond. So keep in your mind, if you have some asymmetric reagent, for one of the end is positive and other is negative, it is asymmetric. Same thing, asymmetric alkene. Like you can see, it is a double bond, and across the double bond you can see right hand has a one carbon, but left hand side no other carbon. So it is not in symmetrical way. Okay. So this positive end, it will attract to the carbon which will bear maximum hydrogens, a more number of hydrogens. So now you can see this carbon, here's a one hydrogen, here's another hydrogen. So this carbon is like direct connected with two hydrogens, but this carbon is direct connected with one hydrogen. Is it clear? So the positive end will attach, I'll write it here, positive or like electrophilic, okay? Positive atom will attach with that carbon of double bond, okay? Carbon of double bond, which is connected with, just connected with like more hydrogens, okay? Is the first point. You can even write this, negative end will connect with the carbon which is connected with the less number of hydrogens, okay? So now let me make their products. How can I make their product? For example, here, so it is carbon. So now you know pi bond will be broken down. Here it has already two hydrogens already. You can see it is a new hydrogen came from HBr, okay? So yellow one came from HBr, okay? So the next thing is, you can see it here, next carbon will become a positive carbocation already connected with one hydrogen and connected with Ca3. You notice a secondary carbocation. Suppose if I add negative here, suppose if I make this opposite product, for example, if I attach this hydrogen here, the yellow one here, you can see it here. If I attach this hydrogen here, okay, so then you people can see you will get a carbocation, the positive charge on this carbon. Is it? So it will give you primary carbocation product. Primary carbocation, it is less stable, okay? It is primary carbocation. But in this case, you are getting like this carbon is connected with two other carbons, 1 and 2. It is known as secondary carbocation. Secondary carbocation. Okay. So secondary carbocation is more stable than primary. Is more stable or major product, okay, than primary, okay. So now you need to proceed with this reaction mechanism, okay. So how I will proceed with this reaction mechanism? Now you will notice like the Br negative of the molecule, so it will react over this, you can see it will attack over this carbon, and what will you get now? So your final answer will be, your final product you will get this CH3 with C then H with this Br with this CH3. So it is your actual major product. Okay, it is your major product. You will get this product as a dominant product. Okay, so here you can see, what about this? You will get this. For example, you have Br negative here. In this case, Br will attach over here. So now you will get this like C with two hydrogens with just one Br here, and you will get this CH2 and you will get this CH3. It will become your minor product. So if there's possibility of tertiary carbocation, that is the preferable thing. Okay. Of course, when I will teach you how to solve their past papers, then you can recall these things over there. Okay. So the next thing is reaction with water, or you can say reaction with steam. Okay. Reaction with water. Reaction with steam. You know, alkene reacts with, for example, now I am trying to make some tertiary carbocation. Okay. I'll just let me teach you guys another way. Like C when a hydrogen connected with further C2H5. Okay, I'm making some difficult for you. Okay, so now you're adding water into it. So how can we add some water here? H and OH is the structure of water. You can see negative and there is a positive. So what is the catalyst for this reaction? The famous one is phosphoric acid. Okay, it acts as a catalyst. Okay, so now what I taught you is like it is the positive end, it is the negative end. Okay, so the positive end now will combine with, you can see this pi bond will first attack over here with electrophile, electron of this hydrogen and with this OH, both they will shift here. Okay, so now you will get this. For example, you will get this CH2 with this CH2. I think there's no CH2. Okay, it will become CH. It's not satisfying the valency. Okay, let me remove. Okay, so now CH. So one of the bond will broken down. You will get this CH. I think that was okay, good. It will become C2H5. So the hydrogen will add with the carbon, which is connected with more hydrogens. Okay. So now you can see it was a double bond here. And this carbon was connected with one carbon, like one hydrogen. And this too, for example, if I remove it from here, so now you can see it's making like double bond. It means it's also connected with the one hydrogen. So now you can attach with any end. Okay. So now it will become like this. For example, it's one of the things you will become like carbocation. I'm adding hydrogen here, it will become your carbocation. And their OH negative, it will attack over this carbon. And now you will get the answer CH2, CH2, CH with this like OH and C2H5. So you get alcohol. Okay. So when you actually hydrate this alkene in the presence of phosphoric acid, you will get alcohol. Okay, it is another famous question, repeated question. So the next question is reaction with, so next type is oxidation reaction. Okay, oxidation reaction. So there are two type of reactions in your syllabus. Number one is, so what is like oxidizing agent? Oxidizing agent for, in this case, it is acidified potassium permanganate. Okay, it is acidified potassium permanganate. Okay. So it is oxidizing agent. It will provide oxygen to alkene. So the first thing is, the first method in your book is actually according to your syllabus. So condition is you are reacting this alkene, carbon to carbon double bond is here. But what is the condition? Condition is you are using number one cold and dilute. Cold and dilute acidified potassium permanganate. It is your oxidizing agent. Okay. So now you will get this diol. The product will become, you will get one of the OH here and you will get other hydroxy group. It is known as hydroxy group. Okay. So you will get ethane diol. Your product is ethane diol. Two OL are there, two groups of hydroxy, alcohol groups are there. Okay. It is simple and easy. Like you have cold, dilute, acidified. But the other one is little bit tricky. When you change this condition, for example, for you are now changing this condition, or now condition is, for example, you have some alkene, okay, and now you, this alkene, you're using, what are the conditions actually you're using here? Let me write in different color. So if you're using the hot and concentrated, now you're using hot and concentrated acidified KMnO4, okay. If you have hot acidified KMnO4, okay, so it means concept little bit will change. Okay, how? So now you have to notice it. Okay, if you have this carbon to carbon, for example, now you need to break this bond here, and this C, if carbon is connected with two hydrogens, so you will get CO2 plus H2 product. And this end, for example, this carbon is connected with two CH3CH3, so you will get this carbon double bond with oxygen and attach with this CH3 and with this CH3. Okay, it is your ketone. You know, when this carbonyl group are direct attached with both sides with carbon, this function group family is your ketone. We will discuss in detail in aldehyde ketone chapter. Okay, so it is like important to know if this carbon, you can see this carbon, hydrogen is here, hydrogen is here. They are like they will break down from here, and if both are sides are connected with the hydrogens, you will get this carbon dioxide and water. So what about other carbon if it is connected with methyl group or methyl with some other even methyl, ethyl group or butyl? So it will oxidize into, like you need to put oxygen here just like this. I have added oxygen here, okay? So still two groups are there, CH3, CH3. So you will get this ketone, okay? So let me explain some like other condition for you. For example, if you have this carbon to carbon double bond, let me like explain with white color, okay? For example, now you have carbon to carbon double bond. Okay, one of them is connected with C2H5, other end is connected with one hydrogen. But this side I am saying like it is connected with CH3, CH2 and CH2, and this side is connected with, for example, CH3. Okay, so condition is same. So what is the condition? What is the condition actually? So condition is you're using hot, concentrated, hot plus concentrated acidified KMnO4. Okay, it is the condition of this reaction. Okay, so now you need to focus like from here, you know, like the bond will broken down from here. Okay, it will broken down from here Okay, and now you will get this. So now see, watch over this carbon. This carbon is connected with CH3 group, as well as it is connected with this C3H7. Okay, so I'm writing it here. Carbon, it is connected with C3H7, C3H7, and this end is connected with CH3. So it is actually, it will become carbon double bond because it is being oxidized, and KMnO4 is providing this oxygen. Once again becomes ketone family. So now if you focus on this carbon, so one of the end is connected with the hydrogen, okay, and other end is connected with C2H5, okay. So plus this carbon combined with this, okay, with this like C2H5, and it will become this with hydrogen, aldehyde, okay. As you know, this carbon to hydrogen bond is easy to oxidize, and carbon to carbon bond is difficult to oxidize. So because you're using concentrated KMnO4 here, so you will get this aldehyde further oxidized into carbon, double bond with oxygen. Here you have C2H5, and now you will get OH, carboxylic acid, okay? So aldehyde further oxidize into carboxylic acid, okay? Further oxidize into carboxylic acid, okay? So what about ketone? Ketone, ketone doesn't oxidize. Is it? What is the reason why ketone doesn't oxidize? Because you know this ketone is connected with carbons, and carbon to this carbon bond is difficult to oxidize. In, you can see like aldehydes, this carbonyl is connected with this hydrogen, and this carbon to hydrogen bond is easy to, you can see, oxidize. Okay, so I hope you people understand this. It was little bit about alkenes. So in next class, I will solve your topical past papers of alkene from 2024 to 2014 for last 10 years. Okay. So subscribe my channel, support me. Allah Hafiz.